Time is not the ticking of a clock, nor the turning of a calendar. It is the invisible current that carries all things forward. It lifts the first stars into brilliance, then drags them into silence. It stretches galaxies across the dark sea, only to dim them in the slow erosion of entropy. It is the silent river in which every atom, every planet, every life is swept along. For most of human history, this river was assumed to be eternal. The heavens appeared unchanging. Stars rose and fell with perfect rhythm, and the cosmos was thought infinite in both space and age. Yet, as telescopes grew stronger and mathematics sharper, a darker revelation emerged. The universe does not last forever. It has a beginning. And with that revelation comes the unspoken truth. It must also have an end. Across mountaintop observatories and orbiting satellites, astronomers trace the fate of time itself. They see galaxies racing away into darkness. They watch stars exhaust their fuel and die. They measure the deep hum of the cosmic microwave background, an afterglow of the universe's first breath, already fading into silence. And in these observations lies a haunting vision, a future sky emptied of stars, a cosmos where light itself will vanish, where time stretches thin, approaching stillness. Imagine. Then, the last astronomers, trillions of years from now, standing beneath a night that no longer reveals galaxies, no longer reveals history, only a void where the universe once shone. They will be the witnesses to the end of cosmic time. And yet, perhaps, we are already the first. The story of time begins with the stars. Long before equations, satellites, or telescopes, ancient astronomers gazed at the night sky and assumed permanence. The Babylonians etched celestial cycles onto clay tablets, recording the risings and settings of Venus as though each motion would repeat forever. The Egyptians aligned temples with Sirius, heralding the Nile's flood as an eternal rhythm. In China, imperial astronomers traced comets and eclipses, believing the heavens reflected the unbroken mandate of order. And in Greece, Aristotle declared, "The heavens changeless, eternal spheres that revolved with perfect geometry, untouched by decay." For millennia, time was measured not in endings, but in cycles, the eternal return of the seasons, the rise and fall of suns, the recurrence of celestial patterns. To those who first mapped the sky, the stars were guardians of an infinite cosmos, unyielding to death or silence, yet whispers of impermanence lingered even then. Heraclitus, the Greek philosopher, spoke of change as the only constant of a cosmos in flux. Ancient myths echoed similar truths. Norse legends spoke of Ragnarok, the twilight of the gods and the collapse of heavens. Hindu cosmology imagined endless cycles of creation and dissolution. In these myths, collapse was not an accident, but destiny. Still, the prevailing vision was one of permanence. Even when Nicolaus Copernicus displaced Earth from the center of creation, the cosmos itself was still imagined as infinite, timeless, eternal. Galileo's telescope revealed the craters of the moon, the phases of Venus, the moons of Jupiter. But the greater universe remained unaged, unending. The stage was rearranged, but time itself was untouched. Then came Isaac Newton. With the Principia in 1687, Newton unveiled a cosmos ruled by universal law, where gravity bound planets to the sun and comets to vast arcs across the void. To Newton, time was absolute, a uniform river flowing independently of the cosmos. Space and time were the stage, and matter the actors. The heavens were not eternal in myth. but eternal in mechanism, a clockwork universe wound once and left to run forever. In Newton's cosmos, collapse was local, an apple falling, a stone dropping, but never cosmic. The stars and galaxies, infinite in number and extent, had no beginning, no end. But the 20th century shattered this illusion. Einstein's general theory of relativity, published in 1915, recast time not as an absolute backdrop, but as a fabric woven with space. Gravity was not a force acting at a distance, but the curvature of space-time itself. Mass and energy bent the fabric. Stars and planets followed the curves. Time was no longer uniform, but elastic, stretching near massive bodies, slowing in the presence of gravity. The eternal clockwork was broken. Einstein's equations revealed something far stranger. They permitted the possibility of singularities, regions where the fabric of space-time collapsed into infinities. At such points, time itself could break down. Reluctant at first, Einstein himself dismissed the cosmological implications, even adding a cosmological constant to force the universe into stasis. He could not imagine a cosmos that was not eternal, but the sky had already written its truth. In the 1920s, Edwin Hubble, peering through the 100-inch Hooker telescope on Mount Wilson, made the most unsettling discovery in astronomy. By measuring the light of distant galaxies, Hubble saw their spectra stretched, shifted toward the red. This redshift meant they were receding, and more than that, the farther a galaxy lay, the faster it retreated. The universe was not static, it was expanding. If space was expanding now, then in the past it must have been smaller, denser, hotter. The cosmos had not always existed. It had been born. Time itself, once imagined infinite, was revealed to have a beginning. This revelation transformed astronomy into something new. Cosmology. The cosmos was no longer eternal backdrop, but mortal story. A universe with a beginning must also have an ending. For the first time, astronomers glimpsed time as a fragile, finite arc. The vision deepened in 1965. Arno Penzias and Robert Wilson, working with a horn antenna in New Jersey, detected a faint, persistent hiss of microwaves, a signal that came not from the Earth, nor the galaxy, but from every direction in the sky. This was the cosmic microwave background, the fading afterglow of the Big Bang. Light stretched thin across 13.8 billion years. The universe itself was radiating memory, proof that it had been born from fire. The eternal sky was gone. In its place stood a mortal cosmos, with a measurable age and a visible history. Astronomers began piecing together this history with tools of light and mathematics. Stars were born in collapsing clouds of hydrogen, burned their fuel, and died. Some gently, as white dwarfs, others violently, in supernova, scattering elements into the void. From their ashes, new stars and planets arose. Collapse and renewal, creation and destruction, written into the cycle of stellar time. Galaxies, too, bore the scars of mortality. Collisions reshaped them, black holes anchored them, clusters of galaxies drifted apart in the expanding universe. The cosmic web stretched thinner with each epoch, and at the larger scale. Astronomers realized they could map not only stars and galaxies, but the destiny of time itself. For if the universe had begun in expansion, its future lay in the balance of gravity and momentum. Would it slow, collapse back into a fiery end, a big crunch, or would it drift endlessly, stars burning out in an eternal expansion? By the mid-20th century, the universe was no longer eternal, no longer permanent. It had a past, it had a present, and it awaited a future. But the most haunting realization was yet to come. For in the dying light of distant supernova, astronomers would soon discover that time's end was not gentle, not balanced, not predictable. It was something stranger, something more terrifying. The expansion was not slowing, it was accelerating. And with that discovery, the astronomers of the 20th century became something more than observers of stars. They became witnesses to the mortality of time itself. The eternal sky had ended. The countdown had begun. The universe was no longer eternal. That revelation alone had reshaped philosophy and science. But what came next would shake the foundations of physics even further. Edwin Hubble's law, the discovery that galaxies recede at speeds proportional to their distance, implied not only an expanding universe, but one born in fire. Time itself had an origin. The cosmos, once imagined infinite, was suddenly finite, with a measurable age, about 13.8 billion years. This was shocking enough. Yet the equations of Einstein's relativity went further, predicting not only beginnings, but endings. They foretold singularities, places where curvature of space-time grew infinite, where physics itself dissolved. To accept the Big Bang as real was to accept that time itself had once been compressed to a vanishing point, a boundary, an edge. The terror of infinities haunted astronomers. In Newton's mechanics, infinities were mathematical curiosities, to be swept aside as impractical. But in relativity, infinities were unavoidable, the natural conclusion of collapse. When a massive star exhausted its fuel, gravity crushed its core, creating a singularity hidden by an event horizon. A black hole. Here, time stretched, slowed, and ended. Singularities were not just abstract, they were written into the death of stars. But cosmology, the shock was greater still. If singularities marked the death of stars, then one marked the birth of the universe itself. The Big Bang was not merely an explosion of matter into space. It was the collapse of all space and time into a single, incomprehensible point. The beginning of everything and the beginning of endings. Astronomers confronted another law, the second law of thermodynamics. Entropy increases, order decays. Stars burn their fuel, galaxies scatter, and energy spreads. The arrow of time points toward disorder. Already, by the mid-20th century, physicists understood that the universe was destined for heat death, a state where all energy is evenly distributed, where no work can be done, where time itself loses meaning. But the true shock came in 1998. Two teams of astronomers, studying Type Ia supernova as standard candles, expected to confirm that cosmic expansion was slowing under the pull of gravity. Instead, the supernova appeared dimmer than predicted. The universe was not slowing, it was accelerating. This discovery overturned everything. Expansion meant the cosmos had a beginning. Acceleration meant it might never end in collapse. Instead, galaxies would rush apart faster and faster, disappearing beyond cosmic horizons. Stars would burn in isolation. The night sky, once alive with countless galaxies, would fade to darkness. This accelerating force was named dark energy. It accounted for nearly 70% of the energy content of the universe, yet its nature was unknown. Vacuum energy, a new field, a property of space-time itself. Whatever it was, it pushed reality toward a fate more terrifying than heat death. A universe torn apart, not slowly, but relentlessly. The implications deepened dread. If acceleration continued, a big rip was possible. Galaxies torn asunder. Stars shredded, planets dissolved, atoms themselves pulled apart. Even space-time could fracture, ending time in a final catastrophic disintegration. And yet, this was not the only possibility. Another fate lurked in quantum theory, the Higgs field. Discovered in 2012, gave particles their mass, but its measured value suggested metastability. Our vacuum might not be the lowest energy state. It could collapse to a deeper vacuum, rewriting physics in an instant. This false vacuum decay would spread at light speed, erasing atoms, stars, and galaxies without warning. Time would not end slowly, but instantly. The universe, once imagined infinite and eternal, now appeared fragile, contingent, mortal. The laws of physics themselves seemed temporary, resting on unstable ground. The astronomers had begun by mapping galaxies. Now they were mapping mortality. They realized that to study supernova, the cosmic microwave background, or the redshift of galaxies was to study the death of time itself. Stephen Hawking deepened the unease. In 1974, he predicted that black holes radiate, slowly evaporating, as quantum effects near their horizons release energy. This Hawking radiation meant that even the most permanent objects in the cosmos would one day vanish. Black holes would shrink, flicker, and dissolve into nothingness. No fortress was eternal. Worse still, Hawking raised the black hole information paradox. If matter falls into a black hole, and the whole evaporates, where does the information go? Physics holds that information is never destroyed. But black holes seemed to erase it from the universe. This violation shook the very foundations of quantum mechanics. Astronomy was no longer only about stars. It had become the study of paradoxes, of infinities where mathematics broke, of horizons where time ended, of laws that contradicted themselves. The scientific shock lay not just in discovery, but in dread. Dread that the cosmos was temporary. Dread that its most sacred laws could collapse. Dread that even time, the silent river of existence, was mortal. For millennia, humans believed the sky eternal. Now, astronomers stood at telescopes and saw a cosmos rushing toward endings written into its very structure. Expansion, acceleration, entropy, collapse. Each observation pulled the curtain further from eternity. The universe was not infinite. It was fragile, it was fleeting, and the astronomers had become witnesses not only to its beginning, but to the end of time itself. The shock of a finite universe, of accelerating expansion, of time with an end. It could not be left as revelation alone. Astronomers turned from awe to measurement, from terror to inquiry. If the sky was vanishing, they would map it before. It disappeared. The first great portrait was painted in microwaves. In 1965, Arno Penzias and Robert Wilson had stumbled upon a faint hiss in their radio antenna, a noise they could not erase. It was the cosmic microwave background, the afterglow of the Big Bang. In that radiation was proof that the universe had once been a fireball, cooling for billions of years. But its details held more, a map of time itself. Decades later, satellites refined the picture. COBE in 1989 revealed temperature fluctuations of 1 part in 100,000 tiny ripples that seeded galaxies. WMAP sharpened the map. Planck, in 2013, delivered the most detailed image yet, a universe 13.8 billion years old, with its density, geometry, and composition measured with exquisite precision. In those faint fluctuations lay the fingerprints of the cosmos's destiny. The cosmic microwave background was more than light. It was a horizon, the farthest we can see, the surface of last scattering, where the first atoms formed and the universe became transparent. To study it was to stare at the edge of time beyond the background. Astronomers charted galaxies themselves. The Sloan Digital Sky Survey began in 2000, mapping millions of galaxies across billions of light-years. The result was the cosmic web, filaments of galaxies stretching like veins of light, with vast voids in between. The structure echoed the ripples of the early universe, fossil sound waves frozen into space itself. These baryon acoustic oscillations became another cosmic yardstick, confirming the history of expansion and the dominance of dark energy. Every measurement told the same story. The universe was accelerating. Dark energy was real, its pressure woven into the very fabric of space-time. But astronomers probed deeper still. If time was to end, they needed to know how. Black holes became laboratories for horizons, from stellar remnants to supermassive giants. In galactic centers, they embodied the limits of time. Around them, matter swirled in accretion disks, heating to millions of degrees, releasing jets that pierced galaxies. Their presence was inferred in X-rays, in the dance of stars, in radio jets stretching thousands of light-years. Then, in 2019, the Event Horizon Telescope delivered the unthinkable, an image of a black hole's shadow. Not an artist's vision, not a calculation, but a direct observation of the horizon where time falters. Light itself bent around the abyss. Mathematics that once seemed abstract was revealed in fire and shadow. Even more astonishing were the sounds of the universe. In 2015, LIGO detected gravitational waves from two colliding black holes. The fabric of space-time itself trembled, carrying a signal across 1 billion years. For the first time, astronomers heard collapse. They heard the death of time written in ripples. Each detection since has revealed new horizons, neutron stars colliding, forging gold and heavy elements. Black holes merging in distant voids. These cataclysms confirmed that collapse is not exception but rule, and they confirmed Hawking's vision that even the most permanent of structures are temporary. Entropy, too, was traced across cosmic history. Stars are engines of decay, turning hydrogen into heavier elements, burning order into disorder. Each supernova, while forging the building blocks of life, also spreads entropy further. Galaxies collide and merge, but always with a loss of usable energy. Black holes consume, but in the end, even they evaporate. The universe moves in one direction only, toward stillness. Yet amid this bleak trajectory, astronomers found deeper paradoxes. If black holes evaporate, what of the information they contain? Hawking's paradox suggested destruction, but physics resists the loss of information. String theory proposed that information may be preserved on horizons, leading to the holographic principle, the idea that reality itself may be encoded on boundaries. A staggering thought that the universe, and perhaps time itself, is written not in volume but in surface. The deeper astronomers looked, the more horizons multiplied. The observable universe had its boundary, the cosmic horizon, about 46 billion light-years away. Beyond it, galaxies recede faster than light, their signals never to arrive. That horizon grows, but it also erases. Every year, hundreds of galaxies vanish beyond reach. The map of the sky is a map of disappearance. In this age, the task of astronomy changed. No longer was it merely to chart stars. It became to chart destiny, to measure entropy, acceleration, horizons, and to ask whether time itself was stable. Laboratories on Earth joined the search. Particle accelerators smashed protons at near light speed, recreating the conditions of the early universe. In 2012, the Higgs boson was found, confirming the Higgs field, an invisible presence that gives mass to matter, but its properties suggested something unsettling. Our vacuum might not be absolute. If the Higgs field rests in a metastable state, then a deeper vacuum exists, waiting. If triggered, the collapse would spread at light speed, rewriting the laws of physics in an instant. The universe, it seemed, was balanced on a knife's edge. From the cosmic microwave background to the Higgs field, from black hole horizons to cosmic acceleration, every observation pointed to fragility. Time itself was not guaranteed. Supercomputers traced possible futures. Simulations ran trillions of years ahead, showing stars burning out, galaxies scattering, black holes evaporating. Some showed heat death, the slow fade into darkness. Others showed rip acceleration, tearing atoms apart. Still others showed collapse, a universe reborn in a crunch. Each scenario was dictated by the same laws, yet none could be confirmed. Astronomers found themselves not merely observers but prophets, describing futures they would never see. Their telescopes measured galaxies, but their calculations measured destiny. The deeper they looked, the stranger the cosmos became. Horizons, once thought distant, grew nearer. Entropy, once abstract, became tangible. Dark energy, once theoretical, became dominant. Every step into data revealed not reassurance, but deeper unease. The universe was no longer infinite, eternal, or stable. It was finite, fragile, accelerating toward fates that science could describe but not prevent. Deeper investigation had not resolved the mystery. It had multiplied it. Time itself was under question. The universe had revealed its mortality. But what followed was worse. The realization that the end was not distant speculation, but written into every observation. The cosmos was not simply aging, it was accelerating toward horizons where even mathematics trembled. The culprit was dark energy. In 1998, two teams studying Type Ia supernova, exploding stars used as cosmic mile markers, found that the universe's expansion was speeding up. This discovery overturned centuries of belief. Gravity, once thought the master force, was losing. Something stronger, something woven into the fabric of space itself, was pushing the universe apart. Today, dark energy accounts for about 70% of all cosmic content. Its nature remains unknown, but its effect is undeniable. It dominates destiny as expansion accelerates. Horizons multiply. Beyond a cosmic event horizon, galaxies recede so quickly that their light can never reach us. Each year, more of the universe slips away. In the far future, only the galaxies of our local group, the Milky Way, Andromeda, and their satellites, will remain visible. Everything else will vanish into silence. Future astronomers, born trillions of years from now, may gaze into a night sky stripped bare, unaware that other galaxies ever existed. The cosmic story we tell today will be erased. This realization deepened into dread. The universe was not only finite in past, but in future. Time itself was bounded by horizons, yet worse fates emerged. If dark energy is constant, the cosmos ends. In heat death, stars burn out, black holes evaporate, entropy spreads until all motion ceases. The last sparks of matter fade into darkness, leaving a silent, frozen void. Time stretches, but meaning dissolves. But if dark energy is not constant, the end could be catastrophic. One possibility is the Big Rip. If expansion accelerates without limit, galaxies will be torn apart. Stars will be ripped from galaxies, planets from stars, atoms from planets. In the final instant, even protons will be shredded by the stretching of space-time itself. Time ends not in stillness, but in violence. Another possibility is false vacuum decay. If our universe is not in its lowest energy state, but only in a temporary equilibrium, then a deeper vacuum may exist. A bubble of that vacuum could appear anywhere, triggered by quantum fluctuations, expanding at nearly the speed of light. It would erase our universe instantly, rewriting physics, destroying atoms, ending time without warning. These are not idle nightmares. They are consequences of known physics extrapolated to their limits. Entropy, dark energy, quantum fields, each carries with it the possibility of finality. The terror deepened with horizons of another kind. Black holes, once thought eternal. Prisons revealed paradoxes at their boundaries. Hawking radiation predicted that black holes evaporate, leaking energy over vast timescales. But if they evaporate, what happens to the information they contain? Quantum mechanics forbids destruction, yet relativity insists on it. This clash produced the information paradox, one of the greatest crises in physics. In 2012, the firewall paradox emerged. If quantum mechanics holds, then the horizon of a black hole may be a searing wall of energy. If relativity holds, the horizon must be smooth. The two are incompatible. At the edge of time, the laws of physics themselves collapse into contradiction. At cosmic scales, horizons multiply further. The accelerated expansion produces a cosmic horizon beyond which no information can return. Thermodynamics implies a horizon of maximum entropy. Black holes hold their own horizons. Each horizon is a boundary not only of sight, but of knowledge. Astronomers, once charting stars and galaxies, found themselves confronting the end of information itself. What lies beyond a horizon may not be knowable, not even in principle. The universe was not only ending, it was erasing its own record. This escalation transformed the mystery into existential dread. The cosmos was no longer a backdrop, eternal and indifferent. It was fragile, dynamic, unstable. Time itself was suspect. The question grew sharper. Is time fundamental or emergent? If horizons erase knowledge, perhaps time itself is only an approximation, dissolving at extremes. Some theories suggest time emerges from quantum entanglement, from correlations between particles. If so, then at the end of time, entanglement itself may unravel. Speculation grew into philosophical terror. Perhaps the universe is not infinite, but bounded in both directions, a beginning in the Big Bang, an ending in entropy, rip or collapse. Perhaps time is not universal, but local to our cosmos. Beyond our horizons may lie other realities with other times. Perhaps time itself is illusion, its ending a reflection of our limits rather than realities. Yet for astronomers, these were not abstractions. They watched galaxies vanish. They measured acceleration. They mapped entropy. Every observation brought the end closer. The escalation of mystery was not confined to cosmic scales. Particle physics suggested fragility at the smallest levels. The Higgs boson's mass, measured in 2012, implied metastability, the possibility that our vacuum is not ultimate. Combined with quantum uncertainty, this meant the universe was balanced on a knife's edge, a collapse waiting to happen, from the largest structures to the smallest particles. Every layer of reality pointed to the same conclusion. Time was not guaranteed. The astronomers stood at a precipice. Their instruments revealed horizons where physics broke, where entropy ruled, where expansion erased. Beyond those horizons lay only speculation. The night sky, once eternal, had become a vanishing act. The stars were not timeless companions, but fleeting sparks. The galaxies, not infinite, but temporary patterns. The universe, not immortal, but mortal. And so the mystery deepened. Time, once the most reliable of dimensions, had become the most fragile. The mystery of time's ending pressed against the limits of physics. Observation revealed horizons, expansion, entropy. But to move beyond measurement, science turned to theory, to speculation that reached into the unknown. Each proposal was both a map and a prayer, an attempt to describe what could not yet be touched. The simplest explanation was the cosmological constant, first introduced by Einstein in 1917. It was originally conceived to keep the universe static, counteracting gravity. Later abandoned, it returned after the discovery of cosmic acceleration in 1998. In this model, dark energy is a fixed property of space-time vacuum energy itself, unchanging, eternal. If true, the universe will expand forever. Galaxies will drift apart beyond visibility. Stars will burn out. Black holes will evaporate. And entropy will spread until nothing remains but a thin, cold mist of particles. Time will not stop suddenly, but fade into stillness. This is the heat death, eternity as silence. But many physicists doubted such simplicity. Why should vacuum energy take precisely the value it has, large enough to dominate, yet small enough to allow galaxies and stars to form? The cosmological constant problem remains the worst mismatch in science. Quantum theory predicts vacuum energy to be 10,120 times larger than what we observe. Something is missing. An alternative emerged. Quintessence. Here, dark energy is not fixed, but dynamic, a field evolving over cosmic time, similar to the Higgs field that gives particles mass. If quintessence slows, the expansion may ease. If it grows, the acceleration could intensify, leading to a big rip. In this view, the fate of time is undecided, written in the behavior of a hidden field we have not yet detected. More radical ideas suggest cycles. In some models, the universe expands, slows, and collapses, only to bounce and expand again. Time, in this vision, is not a line, but a rhythm. Endless cycles of birth, collapse, and rebirth. Ancient myths of eternal return echo in these equations. Yet observations of accelerating expansion challenge the cycle. If dark energy is permanent, collapse will never come. Quantum gravity offers another path. In loop quantum cosmology, space-time is not continuous, but built from tiny quanta, like atoms of geometry. Singularities vanish. The Big Bang may have been a bounce from a previous collapse. The end of time in one universe may be the beginning of another. Death becomes transformation. String theory expands speculation further. In this framework, the fundamental constituents of reality are not particles, but vibrating strings existing in higher dimensions. Singularities dissolve into stretched geometries. Horizons may not be boundaries at all, but illusions of limited perspective. String theory also predicts a landscape of possible vacua, countless universes, each with different laws, born from different collapses of higher symmetries. Our universe's end may simply be one note in an infinite symphony. The holographic principle deepens this strangeness. Proposed in the 1990s, it suggests that the information within a volume of space can be described by data encoded on its boundary. A black hole's interior is fully described by information on its event horizon. Extending this idea, perhaps the entire universe is holographic, its three-dimensional time unfolding from information written on a two-dimensional cosmic horizon. If so, time itself is emergent, not fundamental. Its ending may be no more catastrophic than the closing of a projection. What ends is the display, not the underlying code. Inflationary cosmology adds yet another layer. In the first fraction of a second after the Big Bang, a field of vacuum energy drove exponential expansion, creating the vast cosmos from quantum fluctuations. But inflation may not have ended everywhere. In some models, it continues eternally, spawning bubble universes without end. Each bubble has its own physics, its own time. In such a multiverse, the end of time in our universe is only local, a closing chapter in one book, among infinite shells. Other theories are darker. False vacuum decay looms as a possibility. The Higgs-Boson's measured mass suggests our vacuum may be metastable, not the lowest possible state of energy. If so, quantum tunneling could trigger collapse into a deeper vacuum. A bubble of new physics would expand at the speed of light, annihilating everything. No warning, no survivors. In this vision, time does not fade or cycle. It ends instantly, rewritten by a lower symmetry. These possibilities are not idle speculation. They arise from equations, from extrapolations of known physics. Each carries consequences for the destiny of time. Yet each also reveals the incompleteness of our understanding. Einstein's relativity describes space-time on large scales, but breaks down at singularities. Quantum mechanics governs particles and fields, but falters at gravity. The unification of these theories, a quantum theory of gravity, may be the key to understanding time's fate. Until then, speculation reigns, and beneath the speculation lies philosophy. If time is emergent, then perhaps its end is not destruction, but transition. If reality is holographic, then perhaps the fading of galaxies is not loss, but a shift in perspective. If the multiverse is real, then perhaps there is no single end, only endless beginnings. Yet these consolations sit beside dread. Each theory, however elegant, admits fragility. The universe is not eternal clockwork. It is contingent, unstable, precarious. Time itself may be temporary. For the astronomers, this escalation transformed observation into prophecy. Every theory was a mirror, held up to the sky, reflecting not just what was, but what may come. The cosmos had revealed horizons where mathematics falters, where knowledge dissolves, where time itself may vanish. The question was no longer whether time ends, but how. And so speculation did not resolve mystery, it deepened it. Each possibility, heat death, rip, decay, cycle, bounce, multiverse, pointed to endings both majestic and terrifying. Each carried echoes of human fragility. The astronomers realized they were not only watching the stars, but watching themselves, finite. beings in a finite cosmos. In the silence between galaxies, they saw not only the end of time, but the beginning of awe. The astronomers who dared to ask about the end of time did not stop with speculation. They built instruments, launched satellites, and constructed observatories to push the boundaries of knowledge. For them, the fate of the universe was not a question of philosophy alone, but of measurement of signals carried across billions of years, written in light, gravity, and the subtle trembling of space-time itself. The most immediate frontier lay in the heavens. Telescopes turned into time machines. The James Webb Space Telescope, launched in 2021, opened its golden eye to capture galaxies formed just a few hundred million years after the Big Bang. Each faint smudge of light was more than beauty. It was data about expansion, star birth, and the unfolding of cosmic structure. By tracing how early galaxies clustered and how their light was stretched by cosmic redshift, astronomers could refine their understanding of dark energy, the very force dictating the fate of time. Alongside Webb came a new generation of survey telescopes. The Vera C. Rubin Observatory, with its sweeping 10-year legacy survey of space and time, promised to map billions of galaxies in exquisite detail. Every supernova it recorded, every gravitational lens it revealed, became another clock against which cosmic expansion could be measured. If the universe's acceleration was steady, slowing, or quickening, these surveys would see it. To watch the sky at such scale was to chart the tempo of time's unraveling. Europe's Euclid telescope, launched in 2023, joined the quest from orbit, its mission to measure cosmic geometry with precision unmatched before. By mapping how dark matter shaped galaxies and how dark energy pushed them apart, Euclid aimed to distinguish between rival theories. Was the cosmos ruled by a constant vacuum energy, or by a dynamic, shifting field like quintessence? Across the Atlantic, NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, was designed as a dark energy hunter, probing deep into the accelerating expansion. These machines were more than telescopes. They were seers, instruments built to peer into the destiny of the cosmos. But light was not the only messenger. The discovery of gravitational waves in 2015 by LIGO added a new way to probe time's boundaries. Black holes colliding sent ripples across space-time, vibrations detected on Earth as faint stretching and squeezing of distance itself. With every detection, astronomers tested Einstein's relativity under conditions of extreme gravity. Did black holes behave as theory predicted? Did the waves carry hints of new physics, deviations that might whisper of quantum gravity? As detectors grew more sensitive, from Virgo in Europe to Kagra in Japan, and as plans matured for LISA, a space-based observatory with arms millions of kilometers long, the dream grew clearer, to hear not just collisions, but the deep hum of the early universe, perhaps even vibrations from inflation itself. To listen for the echoes of time's beginning was also to listen for its end. Meanwhile, experiments on Earth sought answers in the smallest of scales. The Large Hadron Collider, buried beneath Geneva, had discovered the Higgs boson in 2012, confirming the existence of a field that gives mass to matter. But it also raised unsettling questions. The Higgs's measured mass implied our universe might be metastable, perched in a false vacuum, at risk of collapse into a lower state, by smashing particles together at energies approaching those of the early universe. Physicists tested whether hidden symmetries or new particles might stabilize the vacuum. The search for supersymmetry, extra dimensions, or exotic matter was more than curiosity. It was an inquiry into whether time itself was secure. Other experiments reached into the dark. Detectors buried deep underground, shielded from noise, waited for whispers of dark matter particles, the invisible scaffolding of galaxies. If discovered, dark matter could reshape understanding of cosmic evolution, linking the structure of the universe to its ultimate fate. Instruments like Xenon in Italy or Lux Zeppelin in the United States strained for rare collisions of dark matter with atomic nuclei. Each silence, each null result, deepened the mystery. Cosmic time was also studied in its oldest light. Missions like Planck had already mapped the cosmic microwave background in exquisite detail, showing the infant universe 380,000 years after the Big Bang. Now new projects, Light Bayard in Japan, CMBS-4 in the United States, sought the faint polarization patterns that inflation might have left behind. To see them would be to glimpse the moment when space-time itself erupted into being. Inflation theory, if confirmed, would tie the end of time to the very beginning, revealing the rhythm of creation and dissolution. Beyond telescopes and colliders, scientists built analog universes. In chilled laboratories, Bose-Einstein condensates were coaxed into strange states, mimicking horizons where sound waves behaved like light near a black hole. These tabletop experiments offered a chance to test Hawking's predictions of radiation from horizons, to see how time's flow breaks down at its edges. In the controlled silence of laboratories, physicists recreated fragments of cosmic catastrophe. Supercomputers, too, became observatories. Simulations modeled trillions of stars, galaxies, and dark matter halos, watching them evolve under the laws of physics. Other simulations stretched further, imagining universes with different amounts of dark energy, different fates, different endings. Each run was a rehearsal for the cosmos, a way of comparing theory against reality. Within these electronic universes, astronomers glimpsed the fragility of our own. All these tools carried urgency. The cosmos does not wait for human comprehension. With every passing billion years, galaxies slip beyond visibility, erased by expansion. There will come a time when the cosmic microwave background itself fades into undetectability, when the clues of the universe's origin and fate vanish forever. The instruments of today are humanity's only chance to record the truth before it disappears. The astronomers knew this. They understood their work as both science and preservation, as drawing the final map of time before its stars went dark. The urgency was not despair, but devotion, to know before silence falls. And so, at mountaintops, in underground caverns, and in satellites orbiting far above the Earth, the search continued. Eyes of glass, ears of laser light, detectors of unimaginable sensitivity, all tuned to the same question. What is the nature of dark energy? Is time eternal or finite? Does the cosmos fade, rip, or collapse? The answers lay not in speculation alone, but in the data yet to come. The tools were built, the skies were watched, the signals awaited. Humanity had reached the threshold where knowledge brushed against mystery. The astronomers were not only watching the universe, they were watching time itself. Time is not only the backdrop of existence, it is the very fabric in which lives unfold, stars ignite, and galaxies drift. For most of human history, time seemed infinite, an endless procession without beginning or end. But the astronomers have revealed a deeper truth. Time is fragile, finite, and bound to the destiny of the cosmos. To gaze at the universe is to see not only its immensity, but its mortality. The story of the cosmos is written in layers of time. At its birth, a hot and dense fireball expanded, cooled, and formed the seeds of galaxies. In its prime, stars forged. The heavy elements scattered them in supernova and gave rise to planets and life. In its aging, galaxies merged and drifted apart, shaped by invisible dark matter, propelled by dark energy. And in its far future, all this structure will fade, stretched beyond sight or dissolved into equilibrium. Time, in its cosmic scale, carries both creation and dissolution. The astronomers who trace this story are not detached observers. They are participants, bound to the same fate they study. Every measurement of a receding galaxy, every detection of entropy's rise, is also a glimpse of humanity's own future. To watch the end of time is to recognize the shared fragility of existence. Stars, civilizations, and lives alike are finite. And yet, within this recognition lies meaning. For impermanence is not the enemy of significance, it is its source. Consider the night sky as it appears today. Thousands of stars scatter across the darkness, their light traveling for years or centuries before meeting the human eye. Beyond them lie billions of galaxies, revealed only through telescopes. But this sky is temporary. In 1 trillion years, future astronomers may look upward and see only silence, no galaxies beyond their own, no relic glow of the Big Bang, no evidence of the vast cosmos we take for granted. They will stand beneath a sky stripped of history. To them, the universe will appear small and eternal, an island alone. The great story will be hidden, erased by time itself. We live, then, in a privileged epoch, a moment when the universe is still readable, when its signals still reach us, when its history can still be known. The cosmic microwave background still glows, galaxies still shine, horizons are still near enough to measure. The astronomers of this age are not only scientists, they are keepers of memory, recording a truth that future beings may never recover. To witness the end of time is also to preserve the record of its beginning. And yet, the mystery cuts deeper. What does it mean for time itself to end? If entropy erases all order, if dark energy stretches space beyond recognition, does time simply become meaningless, an endless stillness, indistinguishable from nothing? Or is time an illusion, a construct born of change, destined to vanish, when change itself ceases? Some theories suggest new beginnings. Loop quantum cosmology imagines a bounce, where collapse turns to expansion and time reverses into renewal. Eternal inflation envisions universes budding forever, each with its own arrow of time. In these models, endings are not true endings, but transitions. Yet for those within a single universe, endings remain absolute. To live inside time is to know it only once, to see its flow move in one direction, from birth to silence. This fragility echoes in human lives. Like stars, people burn brightly, transform matter, create meaning, and fade. Like galaxies, civilizations rise, flourish, and dissolve. And like the cosmos, all stories are finite. Yet it is within this finitude that beauty arises. A universe without death would have no creation. A life without ending would lack urgency, choice, or depth. Time's mortality is the canvas upon which meaning is painted. For the astronomers, the end of time is not despair, but perspective, to measure. The accelerating universe is to know that every star seen today is a gift, every galaxy within reach a fleeting treasure. To study entropy is to understand the cost of order, and to cherish the improbable rise of life within it. To confront horizons is to accept limits, and within those limits to discover wonder. Perhaps the greatest lesson is humility. Mathematics falters at singularities, predictions diverge, and mysteries remain unresolved. The end of time is not yet fully understood. Is it heat death, a big rip, a vacuum decay, or something stranger? Science cannot yet answer with certainty. But this uncertainty itself is profound. It reminds humanity that knowledge is never complete, that reality exceeds comprehension, that awe is not diminished by ignorance, but deepened by it. The astronomers who watch the end of time are not merely predicting a distant future. They are showing humanity its place in a fragile cosmos. The sky overhead is not eternal. The story of galaxies is not unending. Time itself is a chapter, and we live within its pages. To know this is to understand existence not as trivial, but as precious, and so the imagery returns. The last astronomers, in an epoch unimaginably far from now, standing beneath a dark sky. The stars are gone. Galaxies have slipped beyond reach. The microwave background has faded into silence. To them, the cosmos appears eternal, but it is only an illusion, a fragment of a greater story erased by time. They cannot know what we know. They cannot see what we see. The record is lost, but we, in this moment, still can. We live at the edge of revelation, with instruments that touch the birth of time and theories that extend to its death. We are astronomers, not only of the present sky, but of the cosmic story entire. We are, perhaps, the first and the last to witness the universe in its fullness. The end of time may be inevitable. Entropy may spread, dark energy may stretch, and horizons may swallow the visible universe. But wonder is not bound by these fates. Wonder is eternal, because it arises not from permanence, but from the fleeting recognition of beauty. And so the astronomers continue to watch, not to stop the end of time, but to bear witness, to write its story, to preserve its memory, to remind humanity that even as the universe fades, its meaning endures. Time may end, but awe does not. The river flows, the stars fade, horizons close, and still, beneath the night sky, humanity looks, upward, watching, measuring, imagining. At the edge of time, in the silence between galaxies, wonder remains.